It's a pleasure to be here. This is, in some sense, my home community. I'm a computational chemist. I started many, many years ago, before there were supercomputers, and I use some of them. So, and the other reason why I want to thank you is because whenever I get an opportunity like this, it helps me rethink the problem. So in some sense, you've seen the description of my talk, and I've changed it a little as I was writing the presentation. I really decided that I was going to talk much more about if we know enough about the ideas that should frame how to prepare the next generation. So, and I'm going to do that by starting by mentioning a couple of things from other presentations, not from mine. One is the presentation that my colleague Roy P. made at Blue Waters meeting earlier this year about, among other things, computational thinking. And then also some of the work that I have been involved with, a number of people in the audience, Diane, Scott, Renato, Jeffrey Fox, and a number of others, on cyber infrastructure. And I want to do that, then to confront it in some sense, to use it to adapt to what this audience is uniquely set up to do that's not being done. So in some sense, it's going to be a request for help in general. And let me start with this graph that comes from the Science of Learning Center, to which Roy P. and I belong. The goal of the center is basically to understand how the social context impacts learning. And we think about learning not only in the formal education, which is the orange that you see there, but in the sea of blue that represents all the informal way in which people work. And the reason why this is very important is that from the standpoint of society in general, we have a problem in, not only in this country, but certainly in this country, of the preparation of the future generations for work in a world where scientific and technological alphabetization of the population in general is important. I'm not talking about preparing people only for these careers like yours. I'm talking mostly about the need for changing the way we look at how do we prepare people for the society as in general, so that the numbers of people prepared in science and technology that can work in this field grows appropriately. Because the problem is not that we don't have people, it's how people drop out for a number of reasons. And let me use this opportunity to tell you a little bit of the work that I'm doing right now, not because I'm going to discuss it, but because it will tell you the perspective from which I talk. And at the same time, because if any of you are interested, we can talk about this some more. I'm working with the Boeing Corporation and the Santa Fe Institute in modeling the workforce development system of the country as a complex system. Basically, not only the formal education, but how the things that happen outside the formal education, including issues of community and family, help people make decisions that at this time are mostly against science and technology. So we are trying to use complex science methods to understand how to look at the system and develop possible solutions. So that's, in some sense, a perspective that I had in the back of my mind when I was preparing my talk. So what Roy P. started talking, because that, in some sense, I don't know exactly what he was asked to do, except that he was asked to talk about the relationship of the Life Center, the Science of Learning Center, to which he and I belong. And he started talking about computational thinking. How many of you have heard about computational thinking in detail? So there are a large number of people that haven't. So let me then read some of the things that are in here. You can read them also yourself. That it started with Janet Wing, who is a CMU professor of computer science, and then there was a lot of push from other groups about it. But basically what they were talking about the importance of computational thinking as a new literacy. And I'll come back to this because this is what I want to contest in some sense. to foster 21st century workforce development and other broader science citizenry? How can we expand learning opportunities for varieties of computational thinking? And some of the reframings of the issue. So what computational thinking is, according to Janet Wing, is conceptualizing, not computer programming, is fundamental, it's not about rote skills, and so on and so forth. You see where it's going. So it's for everyone, everywhere, not only programming and computer science jobs. Several observations from Roy also on computational thinking. It's about problem solving and debugging, task decomposition, etc., etc., etc. The last bullet is, I have italicized to emphasize it, the emphasis is mine. Only in the last bullet, it talks a little bit about domain knowledge that Janet and the people that are talking about computational thinking bring to the table. But it's obviously to me that the thinking behind computational thinking is to a great degree a thinking that comes from computing, of which this community knows a lot. Mapping on learning progressions in computational thinking, I mentioned this because I will come back to this after I tell you what I think. In the learning sciences of mathematics, physics, chemistry, engineering, etc., we are benefiting from decades of theoretical, empirical, and pedagogical work that computational thinking doesn't have. That's the correlation. We have no counterpart to the Project 2061 Atlas of is actually science literacy for computational thinking. And I will come back to that, because science does have that atlas. Science also has the many years of learning sciences research on how people learn. And although computational thinking is hard, but it's essential intellectual foundation work that a range of fields is concerned with and needs dealing with a computational community. So what Roy goes on to say is that computational thinking applies to the disciplines. It involves simulation and modeling, data capture, handling, environmental sensor concepts, for example, etc. And that awful thing at the bottom, TPCK, I think it means technological, pedagogical, computing, or concept knowledge. So, let's see. I want to emphasize that the simulations and modeling is what I'm going to be talking about. But if you think about all the things that have been said about computational thinking, it's algorithmic thinking. Basically, it's thinking about a process by which we solve problems, which is very much computer science oriented in some sense. Not that it's only used in computer science, but that it is the formulation, the conceptualization of computational thinking comes mostly from computer science and leads to a transition, this is also from Roy, to computational science models. So we have the connection that is being made between computational thinking and computational science, which is something that we have been talking for a long time with a number of you. And this is something that Roy loves, which is making a cloud of the words. But if you look about it, you can see its origins in computer science. So that's one of the things I wanted to bring as background to the status of discussions about issues of science and thinking in terms of education, the discussions that are taking place. My personal view is up to this moment, nobody has really picked up strongly computational thinking as a way of using it in science. What is taking place is similar to what is happening or has happened with complexity science, that people look at it as a new science, not as a different way of looking at the science that we have, which is what I want to talk about. The other background for what we are talking about is a task force, an advisory task force that was created by OCI with recommendations for the whole of NSF. Again, a number of us here have been involved, Diane, Jeffrey, Scott. Always, if you realize, it's more or less the same task, the same group of culprits. One of the aspects of that of that task force, one of the subgroups was cyber learning and workforce development. It was a task force, was cyber infrastructure, workforce development, and higher education, led by Jeffrey Fox, who is here. And the reason that I mention is because their concept of C4 and the discussion that they have has not received the visibility that it seems. So I encourage all of you to look at that, because it deals very directly with the things that you are doing, and it's a way of conceptualizing it differently. What I'm going to talk about is the group that I was in, which is cyber learning, which we took it as research on cyber learning. Remember, this is a task force on workforce development. And there are two ways in which one can interpret workforce development. One can interpret it as the workforce for this community, for preparing people for this community, or you can look at it as a way in which Boeing is looking at it, which is how do you elevate the number of people that do science and technology. So eventually Boeing has more people to hire. But it's not about preparing people for specific jobs. You have the list of people that were part of the committee. Renato Figueiredo, which I hope is someplace around, and myself co-chaired that group. I'm happy to say, I'm going to talk a little bit about the recommendations, but I'm happy to say, not that they are based on the recommendations we made, but if you look at some of the newer solicitations from NSF, you can see the same kind of thinking and the same kind of terminology. Of course, I can stand here and say that it's the impact of our recommendations, but I'm not going to say that. I'm just going to say that basically it's in the air, and everybody picks it up. So what it talks about mostly is a promotion and support of a new cross-disciplinary community that will perform not only the transformative research, calling all the reports that you care to read, which for cyber learning is multidisciplinary in definition, but also the work of translating the research from use by an increasing varied research development and implementation communities. NSF needs to have a leadership to bring this, should include the development of system strategy for encouraging a cumulative of outcomes, and I'll come back to this, from the work, including the integration of proper assessment implementation of cyber learning software. Even by that small amount of work, which something that I was talking before with Gerhard Klimek from NanoHub, it's extremely important contribution to the development of the field, is instrumenting the things you do, particularly in education, but not only in education, I'll tell you in a moment, so that the data is there to think differently about how people learn, and how people learn deeply, not how people learn to end up marking things in multiple choice tests, but end up understanding so that they can apply it in their work. The other recommendation, the transformative nature of the recommendation arises for the need to create, in a timely fashion, a new generative interdisciplinary thinking that can take full advantage of advances in the disciplines. The merging of knowledge and insights of the two communities that are moving fast, but in different directions. One is the one that you represent in some sense, and the other one is the cognitive science and advances. People learn differently, and simulation and modeling have not been studied from the standpoint that all of you know deeply. They have not been studied enough with respect to learning. And without your contributions to that discussion, the things that will happen in education will not be so good. So this is where we are. So where we go from here. The first place, I couldn't resist this. The facts are coming. Okay, and the facts are, and it will come back to this, there are two types of facts. One is that computational thinking is not gaining any traction. The other one is related also to computational thinking, but more, that we have in mind a very, very complicated series of models and a way of using data and thinking about data that we assume the students get from the way we transfer it to them. What the students get is an extremely simplified way that doesn't transmit the complexity of the science. And why is this important? If you think about this, if you look at the clouds, and you can see a movie of the clouds moving, you can see how a tornado comes up with. starts happening. You have no idea of what is forming the tornado, because all the science that we know is at the micro level, and what you're seeing is at a very macro level. So one way of solving the problem is talking about animations. Animation students do not believe, because they shouldn't necessarily. There is a lot that goes between the reality of what we know and the animation. Students do tend to believe more, and this comes out from some work in chemistry education that I have done, since I'm a chemist. The lower picture, which is a scientific visualization of a tornado, identifies the concepts within the data, takes out from the data, visualizes not only the tornado, but the concepts and the movement of air that goes in there. You realize that this is a much deeper way of understanding the concepts in the formation of a tornado that we should be using in education. We don't need to start from the traditional science. We can start from data of this type and use it to help people understand much better what goes on within the very complex scientific phenomena that we deal with. So to give you an idea of why I'm going to be talking so much about models in what rest of my conversation, I want to bring an example that has absolutely nothing to do with this science. It's an anthropology, ethnography example. Before the Second World War, the government asked Ruth Benedict, who was an anthropologist, to do a study of the Japanese society so that they could, in dealing with the Japanese, understand the way the Japanese think. Ruth Benedict knew nothing about that kind of study, so what she did is a study that led to this very famous book, very influential book, Patterns of Culture. What she did was, in the United States, take two communities, the Hopi and the Blackfeet. For the Hopi, the leaders of the society are the elders that are the peacemakers that have all the tradition. They are the anchors of the community. Everybody else is behind. For the Blackfeet, the leader of the community is the most aggressive soldier, the one that has won most battles, and everybody is behind. So her comment was that, in the first place, the people that are outside a society, in one of them, would be the leaders in the other. So it's not a question of the people, it's a question of the culture. And also that when we look at people, we forget that everything we do is translated through models. So, for example, even when we do not simulate, we build, use, think with, and discuss models. And this is something that people, in general, even students, take a long time to develop an understanding of how models are central to the way that science is done. And to finish that thought, let me add that, for example, what science is basically is data-based argumentation. The other thing that people do not understand is the difference between a measurement and data. When I look at my watch, I know whether it's the right time or not because of what I see here, but because I have compared it with other watches. There is a process of validation of measurements that leads to data. So for me, there are two concepts that stand in the way of the citizenry understanding the work that you do and the importance that it has. One is the fundamental role of models behind everything we do. We do not measure things. We do not measure time. We do not measure current. We do not measure anything. What we do is take a measurement that is connected by a long series of explanations and models and theories to the concept that we say we are measuring. This is what people, one of the things people don't understand. And the other one is that any measurement is not data, that you need to accumulate a number of measurements and then do some analysis to understand what is data and what is not. So that's basically, for me, the difference between computational thinking and what is missing. What is missing from computational thinking is, before you can do computational thinking, which is algorithmic, you need to understand about models, which are conceptual. And this is something which this community knows very well. The process of scientific visualization is one of identifying the core concepts within the data concepts that are based on theories and on algorithms, but identify the core concepts in the data and show them visually so that people can, you yourself don't look at the numbers and understand as much as you do when you do a database visualization. So I'll change a little bit of gears right now and talk more about modeling and the things that I hope this community can help do. And Albert Einstein said once, and I think this is absolutely critical in the areas that we are talking about, everything has changed but our thinking. The way we teach has not kept pace with the way we do science. And since I'm a chemist, I'm going to start by talking about inspirational chemists. I wonder how many of you have seen the editorial in Science by Harry Gray and other chemists about basically chemistry does not receive the recognition it merits in terms of its overlap, bridging, not so much overlap, but bridging between other sciences. And it takes a back seat to our thinking, which is based on the traditional paradigms of physics and mathematics. We can talk about this, but we have been thinking about, for many years, about physics as a paradigmatic science. What's taking place right now is that there is a move towards thinking of biology as a paradigmatic science. Biology is physics traditionally, paradigmatically, not that the physics is like that in reality, is reductionist. It's only the nature of the components matter. In biology, it's the relationship between the components that matter. So let me do the same thing that I did before and interpret this in terms of modeling and simulation. My concern is that people talk about modeling and simulation as if they were similar. But to understand simulation, which is algorithmic, what you need to do is understand modeling, which is conceptual. So my challenge to you, and the reason for my talk, is to say to you, how do you collaborate with people that have done all the research? You see, the people that do learning sciences research use modeling and simulation as more or less as a black box, and in a way that does not reflect the deep knowledge about modeling and the use of models that this community has. Roy said also that we have no counterpart to Project 2061, and I will have, I think, say something about that. In the first place, even from Peter Denning, computational thinking is not the solution for computer science. It's a very, very positive step towards expanding the meaning of computer science, particularly the meaning of computer science for other disciplines. There was one thing we used to say at NSF when I was there in EHR, that were two directorates at NSF that have within their own research tradition, within the directorate, a tradition of service to others, and those were education and computers. So computational thinking is a big step forward, but it's not the solution for computer science, nor is the solution from science. What you have here is a way of showing you the nature of the AAAS Atlas of Science Literacy, which if you haven't seen, I recommend strongly that you see, particularly those of you that teach. What the Atlas does is take a number of central concepts in science, like energy, conservation of energy, probability, and things of that nature, and create at each of the levels that you see there are pre-K, K, middle, high school, and so on and so forth. And for each concept draws a map of how it builds from things that people know, and how the things that they know that are different from each other coalesce towards a number of concepts. So it's a way of understanding science as it relates at deeper and deeper levels. Between the cognitive science, cognitive work that has been done on teaching science, and things from the Atlas Literacy, we are in a position to do much more, which we don't do, and this is my point. Because we know that the sciences are in reality a science. Think one of the reasons that the whole area of science and science standards is so problematic as compared to mathematics, where the fact that there are people that complain mean that things are changing. In science, there is not such a complaint because things are not changing. And the reason why things are not changing is that each discipline goes and says, this is what I need need to teach. This is what I need to teach. This is what I need to teach. And they argue among themselves about what is it, who takes more time, and so on and so forth. What we should be doing is saying science is science. We have chemistry, we have physics, we have biology. It so happens that at the nano level they are merging. And they're merging, among other things, because we have new instruments that give us new data that allow us to think about new models. So for me, sciences and the things that we can really should be talking about are experimental research, the issue of data, the measurement is not data, computational experiments, the use of models, the use of data and database argumentation, systems change, forces, models, scale, they're all common to all the sciences. If instead of teaching physics, chemistry, and biology, we were to take the same concepts in chemistry and physics and in biology and in mathematics and in geology and in engineering, the students would see the nature of science in a much deeper way. And I'm sure that most of you work in a multidisciplinary sense, but don't necessarily teach in a multidisciplinary sense. So, and one additional advantage, this comes from Richard Dashel, who is a learning scientist that has done a lot of very good work on science education, commissioned by the National Research Council Committee on the role of laboratory in high school science. Laboratories in high school science, you know, for the most part are useless because they're repeating recipes. But what the point that Richard Dashel is making is that increasingly experiments are increasingly about data and data modeling. So you see that there is a very direct link between the work that you do and the work that should be taught not only in high school but before, but certainly in high school. The thing is that nobody has conceptualized it to the same level that computational thinking has been conceptualized by the computer scientists. So I'm not going to read all of this. I can, you can read it there. But I'm not necessarily talking about learning using models, but learning also making models. It's a deep understanding of the role of models. Everything we do is interpreted through models. If you see a person dressed in black in this society, you assume it's in mourning. Not now maybe a New Age person, but New Age person have other characteristics that allow you to recognize them. Black is for us, in dress code, is death. In other societies, white is the when we see something, even things as simple as that, and I can give you many anecdotes, we are using mental models and we don't know it. So the differences between models and simulation, this again comes from Judah Schwartz, who is a mathematician at Harvard that did some absolutely beautiful work a number of years ago. And we are talking about, for example, there, the purpose of models is to abstract experience, and the purpose of a simulation is to reproduce experience. What we have to teach people is not how to reproduce experience, but how to abstract experience. Models seek to explain, while simulation seeks to describe. The understanding in a simulation comes from your mind and the models that you have in mind that are reflected in the model. And you can keep on reading this, but the issue for me is very simply that the use of models can be used to help people abstract things. Also understand that models are models for a particular purpose. Somebody said, Claude Sherrington, I think it was, that said, if you ask me for a good model of the brain under concussion, I can show you a dish of cold porridge. That's a good model. If you put within the brain cage the equivalent of a dish of cold porridge and you shake it, you're going to have some of the things that happens in a brain when you shake it. Certainly not all of them, because models can become better and better and better. And I don't think I will want to get into this unless you want to talk about it. But in terms of making science acceptable and understandable to the public, think about climate science, all the problems that it's having. People, it's not that they don't believe necessarily that the results are there. Are some people that do not believe that the results are real, but people do not understand that they come from models, that the models represent this part of the reality, and how do we use them, and how do our predictions as scientists keep on changing. Without understanding that science is database argumentation, and that the argumentation and interpretation is based on models, we are lost. So let me give you an example of a very good group that, from which a number of you, I'm sure, are part, that is taking the right steps towards coalescing a community. This is a NanoHub. Gerhard Klimek is here, and I must commend NanoHub for the wonderful job of community creation and community building that they have done, and the deep thought that goes into these things. On the other hand, I want to point out that a lot of advances in nanoscience, nanotechnology, come from the cumulativity that takes place around NanoHub and the people that are looking at nano issues. NSF has understood that, I hope, by funding NanoHub for a number of years. You cannot get the same things of the applications of science to education in the large scale without creating a community that is devoted to the issues of science education based on real science as it's being done now, comparable to NanoHub. And that doesn't create. So one of the problems that we have, and I think it's represented in some of the things that conversations that I had with some of you when we were talking about issues of developing the workforce, the cyber infrastructure workforce. There is no cumulativity. So this is sort of a hope that not only NSF, but all of you understand that there is a lot that is known that cannot move forward without your collaboration as scientists, not as computational scientists, as scientists that do science. It's not only the computation that matters, it's the models that you have. So going back to the cyber learning advisory recommendations, the new cross-disciplinary community between you and people that do cognitive science and learning research is an extremely important thing. I'll give you an example from NSF that is sort of, it's an example that's not a positive example, but it's not, it's an understandable example. For many years, EHR had funds for adding to centers that were funded by other parts of NSF, an educational component. What had to happen was the person that wanted to create that component had to talk to somebody at EHR, and then there was a transfer of knowledge, and ended up with the people in the centers or in the projects that were from the other parts of NSF, understanding a little bit of how to do education and being in touch with education researchers and so on and so forth. When NSF decided that the issue of impact, the second question in the review process, was to apply to everybody, not only to those centers, the money left EHR and went directly to the centers. And lo and behold, what happened? Some of the most stupid things that you can imagine happen about education coming up from the centers. I'm not going to say any from this podium, but I'm willing to say some afterwards. What it came up in my mind is a total hatred for the word outreach. Outreach means we know this, and we used to say in NSF, we throw it to you over the ransom or the transom. Or another way of saying it is we put it out there and somebody will come and pick it up. All those things have resulted in not having the significant changes to science education that should take place. So there are two things in here, one that I highlighted and the other one that I haven't highlighted, which I should have, which is this: every software piece that you use, not only for education but for many other things, should be fully instrumented so that we know how people use it and we can understand, then do the science, do the analytical science, to understand how people think with simulations and think with data. Those are things that this community can do that nobody else can do. So here is exactly the same thing. And this is an editorial from Nature from May of this year about the issue that you should not only publish papers, but value judgments. The value judgments that the Nature is talking about are the value judgments that I'm trying to talk to you about, perhaps not in the same way. There is an example that I will mention, which comes from this other study, which is it's also from this year, about the public failures of climate science in the US. It's not that climate science has failed. What they say is that it failed if you think in terms of communicating to the public what it means and why it is important and why it is believable. People do not believe it because they don't understand that the fact that this year is warmer or is colder in this part of the country is not contrary to the predictions of climate science. This is a fundamental issue. People think that measurement is data, that an individual example is data. On the other hand, what they say is that in terms of science, climate science has done a lot of very good work, and it's a success. But it's not a success in the eyes of the public because precisely the public doesn't understand data, doesn't understand evidence, the use of evidence, doesn't understand models, so they don't understand data-based argumentation based on models and data. And if we were to take that as a marching flag, as a community, we would be doing a lot of good. So, going back to this issue of computational thinking and cyber infrastructure, this community is left out of that discussion. The science that you do is left out of this discussion, and it shouldn't be so. And it shouldn't be so for things like this is a little older, this is from 2001. But stakeholder values and scientific modeling in the News River watershed, someplace in North Carolina, I think it is. The issue is that when you do things of that nature, the stakeholder group, go back to the image of the time people spend in formal education as opposed to the time people spend not in formal education. In informal education, just living and learning. Though people have importance in terms of the support that you receive, but also in terms that for me are much more important than just the support. Without, in the 21st century, let's say, in the 20th century, alphabetization was absolutely very important, in the 19th century as well. If a non-alphabetized society was very different than an alphabetized society. Then mathematics started being added to alphabetization. There was some mathematical alphabetization. My position and that of many, many people is there is no democratic citizenry in the 21st century without a much larger increase of scientific and technological literacy. So there is a social need for the general society for its well-being. There is a social need for the preparation of the next generation of technologists and scientists. And there is a social need for individuals to lead constructive and productive lives in the society, which is not being fully open. So. If you could pick up some of the not only the thinking, the push behind computational thinking and the issues of cyber infrastructure for society, you could do an awful lot of good work. And I go back to saying that it is basically the fact that there are new sciences that are not necessarily being taught. I was part of a group, by the way, the National Nanotechnology Science and Teaching Center for Science for Learning and Teaching has done some work in this. I was part of a project with them and with Boeing for understanding how to include the concepts of nanoscience, which essentially were the concepts of science that I said before, within physics, chemistry, and biology. And we have, you as a group have the tools to do this. I will end up with the graph that I took and modify a little bit from nanostellar. What we have when we change scale is we change models. So for me, this is a representation of thinking what would happen when we have, not only we have the models at different scales, but we have the connections between them. If we were to use that to teach chemistry and physics and biology, using models and how the models change with scale, we would be very, very much ahead in terms of scientific literacy for the population as a whole. And that's all I wanted to say. I certainly hope I can talk some more. I prefer to answer questions and I hope there are many questions. You don't have to agree with me to ask a question. My ego is in a different place at this age. So I must, as a graduate student told me once, I am in a post-CV stage, so that's what else? So thank you very much, and I hope you have some questions and doubts about the things that I have said.
So there are some microphones here. If people have questions, if you can come to them, let us know who you are and ask your question.
Thank you very much. I enjoyed the talk. So I had a question. It seems like you're promoting education focusing on models rather than on simulations.
Yes.
Could you give an example maybe to help me figure out exactly what the difference is between a model and a simulation? So like, could you give an example of a model and then an example of a simulation?
A simulation is based on a model, and it's very useful to describe what happens. When you build a model, you have to think about the concepts and the things. So when modeling and simulation are used indistinctively, it's an assumption that you're using a simulation of a model to show something. But you could think about models without a simulation. That's why I gave the example of the disk of cold porridge. And the fact that I'll tell you an anecdote because we have time and I think illustrates, well, doesn't matter about that anecdote. The problem is that everything we do is interpreted through models, and we don't understand that. And it's not only in science, it's in everything. I mean, why is this telling me time when the physicists don't even know what time is or don't agree on what time is? It's telling me the time because there's a model about how we represent time. And by the way, not every society represents time in the same way. You have societies where time is not a continuous moving forward, but it's a series of isolated steps. So the fact that this tells me the time has a lot of conceptual models behind it. Doesn't mean I have to simulate it to understand the models behind it. So one is to describe. The other, particularly if you build, is to understand the concepts behind it, which is the thing that matters to me.
You've given us quite a challenge.
Tell us who you are.
I'm Diane Baxter, and I'm from SDSC, San Diego Supercomputer Center. You've given us a fairly terrifying challenge, I might say.
Not terrifying.
And it's a very important challenge, but I want to ask you, because you probably do have the insights from history. Project 2061, which you described, and which yielded one of the most exciting documents I've ever read in my life.
Yes.
Came about because a community recognized a need, but they also had a process for pulling together the insights of this larger community, and a process for communicating it in a way that was credible and that led to national action. How do we get that movement and clear vision for this community?
First of all, and I don't know how much the Atlas of Science Literacy is used. Certainly it's not used as generally as it should be. It's not reflected in the standards for science education, and there are two reasons for that. One is that the disciplines go to the standards independently. That's a major, major issue. The other one is something that we can think about, and I can give you an example of why, which is the fact, for example, of all the wonderful, wonderful textbooks and software that NSF has developed in science education, science and mathematics education, it takes 20% of the market and no more. Because the public in general don't understand the difference. That's one of the things that happen. And let me tell you why I think the importance of goals and to have the issue of the citizenry as a goal. When Sputnik was launched, there were a number of very interesting things that happened. I was just reading a history of, there's a new book that came out about the National Defense and Education Act that tells the story very nicely. But when Sputnik was launched, money was given to NSF to develop programs that would train the next generation of scientists and technologies. The books that NSF published, developed by some of the best scientists more interested in education at the time, were lovely. And I'm sure many of you of my age or a little younger still remember those books with warmth and adoration. But what that thing did at the same time is establish that science is for the best and the brightest. And that's the lesson that we are still fighting against. So for me, the issue is, how do we move, how do we tell? What this community can do is tell the people that develop not only the standards, but the public and the parents that will eventually push for those things, that science has changed and we cannot teach science in exactly the same way. If we talked among ourselves, it won't happen. So for this to happen, it has to be much more open and has to be known. For example, how many of you talk with science journalists explaining the importance of the things you do? Not the importance of the computation and the simulation, but the importance of society, of why you use it, and how should it be described. So it's part of the task to be done.
Thank you very much. My name's Les Button from Corning Incorporated, and one of the challenges I see here, let me start by saying I completely agree that you can't be successful if you don't know the difference between modeling and simulation, and if you don't understand the domain you're trying to model. So there's a set of steps there. But to use some of these more sophisticated computational tools, where do you learn it all? If you still have to know all the science and all the modeling and then learn the simulation techniques as well, how do you beef up that big blue bar that you showed at the beginning of your talk, where I don't think you can do it in an academic career. You can't be prepared enough to do it all. So
because we think in terms of preparing people in such a way that you only understand the problem when you finish your PhD. I'll tell you an anecdote. A colleague, a computational chemist, I don't know how many of you remember the crazy Italian Enrico Clementi. You remember him. That was good for him. That was senior scientist at IBM, and he made a videotape that I have lost, and if somebody has it, I would love a copy, of water from atoms and molecules to fluctuations in the Chesapeake Bay. And he used to give the following examples. He says, think about a thin tube, and we are trying to understand the movement of a fluid through the thin tube. What we have are closed-form equations that are so far away from what happens really in a thin tube that engineers don't use them. If you start having a little bit of more computational power and start describing the monolayer that is absorbed on the walls of the tube, eventually you don't have a closed-form equation anymore, and you start having things that can be solved only numerically. And then he went to say, and imagine that you have the obscene amount of computer power that I have at IBM, which by now should be nothing, but you have the obscene computer power. And we start representing the interactions between the atoms in the molecules in the fluid with the atoms in the molecules on the outer monolayer. We are looking at the macro issue from a micro standpoint. That's where we understand the forces. And several things happen when you do that. First of all, it's totally numeric. There's no other way of doing it. The second thing is that you start being able to reflect time and the appearance of a vortex, an eddy at the end, which you couldn't if you don't have time and you don't have the micro relations, you couldn't. And he said something else, but what you have is physics for plumbers. And his point was that we can start teaching fluid dynamics that way. And there will be approximations that are made, but it will not be the same approximations that we make. So one of the projects that I loved the most that I funded while at NSF was done by 2 chemical engineers that were the top people at Berkeley and at MIT on chemical engineering. One had been thinking about teaching for a long time. The other one was the author of the simulation language that was used for consulting by chemical engineers. So what he proposed to do, that the reviewers loved it, I loved it, it was a success. I have no idea if it's being used at all or not outside MIT. What he took is his language, put it on a PC, simplified it a little bit, of course, and added pedagogical scaffolds for it. And then, so he wanted to use it in the first year because he was losing too many students to the mathematics. And he said, if I have students that understand chemical engineering, okay, then they will know what mathematics to learn and why it's important. And he took that program, used it in this way, and went through all the other faculty members that taught the other courses and said, if your students were to think like chemical engineers, how would you change the way you teach? So instead of saying, we need to wait until the end, when they know everything, to do it the way we have done it in the past, we can start by telling them how we think about the problem, and then give them the tools to modify them if they're going to be professionals. If they're not going to be professionals, then they will understand the system, which is what we want. That's my suggestion about how, besides what I'm saying, by saying that there has to be a cumulativity of knowledge and a multidisciplinary community, is that many of these things have not been researched because you as a community have not pushed for research into these issues as such.